only been introduced like twice in my life, so that was cool. All right, I'm gonna share my screen. You guys can see my nice jargon-heavy title here, and I'm also gonna open up the chat just so I have it. Okay, so I want to start out by saying a couple things. First, IRL, I speak very quickly, and it's something I have to consciously remind myself of to slow down. And then when I start teaching, it gets worse because I forget that I'm supposed to speak slower. So if I start like going down at, I don't know, like 90 miles per hour, like, and you're like, I don't know what's going on, please just let me know and I'll try. Second thing, was, if you have a question, like, please just interrupt me to ask it. It's a lot easier to do it in real time than like 50 minutes down the road and people are like, that one slide 20 slides ago. I'm like, oh crap. Yeah, please just interrupt. And I don't know what the like norm is here. Like, I'll be trying to keep an eye on the chat. But if you want to like unmute and ask a question, that would be fine too. I don't know if that's like normal here, so I'm gonna say it's okay. So first of all, I will be talking about some of my research today, and this is a really jargon-heavy title, but it's basically that there are lots of different steps of planetary formation. I'm looking at the last step, which is things smashing into each other, and then I'm also looking at, after they are done smashing into each other, how they're going to evolve dynamically. And specifically the planets that I look at are called super Earths, which are mostly terrestrial planets that are just like more massive than our Earth. But that'll be thoroughly defined. All of this will be. So the reason that I asked about the reading is because one of them was just on planetary formation, but I'll just spend like a little bit longer on this than I would have. So back in the 80s, we came up with what's known as the nebular theory, which is this idea that our solar system formed out of a collapsing cloud. And this cloud was a molecular cloud. It was kind of cold. It had a lot of mass in it, and it had a lot of gas and dust in it, where dust is the generic astronomy term for anything that isn't gas. So we had this cloud, and it was gravitationally sort of stable in the universe and just kind of chilling there until something caused it to change. And we don't know what that something was. It could have been a supernova explosion. It could have been like, I don't know, another galaxy passed by and tidally disrupted this cloud. But something happened, so the cloud started to collapse in on some kind of overdensity. So there's some part that has more mass and therefore more gravitational force, and the cloud started to collapse. As it collapsed, to conserve angular momentum, it started spinning up. Think of like pizza. And it created a disk, and it's from this disk that our planets are going to form. So this gas and dust cloud was made of gas and dust, and there was a point in the solar system formation where our sun started fusing hydrogen. And as soon as that started happening, all of the gas was essentially removed from this whole system. So if planets formed before this part where our sun is becoming what's known as the main sequence star, I don't know what your guys' background is, but if planets formed before the gas was removed, they're going to have really nice, glorious atmospheres like our gas giants, like Jupiter and Saturn and Uranus, Neptune. And then after the gas is removed, we can start forming our more terrestrial planets. And so this kind of like dichotomy between terrestrial planets and gas planets has to do with the sun's evolution and also with how mass was distributed and a lot of different things. So this story, this nebular theory, was all well and good. It readily predicted the different compositions of our planets and how they like lead from like terrestrial to gas to like some icy things out beyond Neptune. I predicted that our planetary orbits would all be fairly circular. They wouldn't be doing anything weird with their orientation. And so that was all nice and well and good. But this was in the 80s, and we updated a little bit in the early 2000s. But this was only informed by our one solar system. And so when we started finding other planets around other stars, things got a little messy. And we'll talk a lot about how that has changed in a bit. But first, my work deals with exoplanets. These are sometimes called extrasolar planets, but that term has kind of been like, I don't know, shoved into the past a little bit. And just as a generic definition, an exoplanet is any planet that is orbiting a star that is not our sun. And so something that a lot of my students get at me at is that when I describe something as a planet, I mean that basically it's not a moon and it's not a star, but anything else is a planet. So like what we consider asteroids or dwarf planets in our solar system is just a planet elsewhere. And here's Pluto being adorable as it was reclassified as a dwarf planet. So most exoplanets that we have today were discovered via the transit method, which either if you didn't know or as a reminder, if we are observing the brightness of a star over a long time period, and if one of its planets passes between the star and us, between our line of sight, we're going to observe a net dip in the brightness of the star. So this GIF is showing this with our sun in the nice UV here, but from this we can come up with the orbital period or the year of the planet, and also the planet's size relative to its stellar host size. So as you can see here, there's an Earth-ish planet that goes across, and then a Jupiter-ish planet that goes across, and the Jupiter-ish planet has a larger signal. So when I say most exoplanets, I mean like 70-something% have been discovered via the transit method. And I'm not going to talk about any other methods because this is what I used for my work. Okay. So the Kepler Space Telescope was launched in 2009, which for me was like recently, but I'm getting old now, so I don't know how like long ago it's considered now, but this telescope and its mission are responsible for most of the planets we know of. So I have just this nice histogram here, so who doesn't like histograms, of a number of planets on the y-axis and then the year of the planetary discovery on the x-axis. And so you can see that before launch of Kepler in 2009, we knew of like, I don't know, 150-ish planets, like 200 reaching that. But once Kepler started getting our data back, it completely threw all of this out of the water. And this is even, like this GIF here is even outdated because Kepler has continued to find more planets after this. So I'm going to study almost all of these planets. Okay, so Kepler found some really weird things which have brought into question our understanding of planetary formation. The first thing that was discovered about exoplanets, which to be fair was not just Kepler, but the original radial velocity surveys, was that we found some really, really hot planets. There are planets whose orbital periods or their years were a day, a singular day of them going around their stars. And for like additional context, Mercury, our innermost planet, has an orbital period of 88 days. So it was way smaller than Mercury's orbit, which we consider to be a very hot orbit. In addition to this, the planets that we were finding were very large. They were like Jupiter-ish in size, about half a Jupiter mass to like 5, 6, 7, 8, 9 Jupiter masses. And so we had these like giant planets that were super close to their stars, and that completely broke all of our theories about planet formation. We did not consider it to be possible, and yet we found tons of them. I'll show you a nice graph of how many I mean by tons. The second thing that we found was completely new types of planets. So what I'm plotting here on the y-axis is the planetary size in relationship to Earth's radius, and this is log scale. I have marked Earth, Neptune, and Jupiter just for guidance. And then on the x-axis is the orbital period. And I want to point out that this graph, by the time we get to like where the color bar is, that's just 300 days. So we haven't even reached Earth's orbit yet by the time we get to the color bar, and we have all of those planets. So we have those really hot planets that are super close to their star, and because we're really creative, we are going to give them a new name. And that new name is going to be hot Jupiters. I went ahead, sorry. So we have hot Jupiters, and those are like, really, we have no idea what's going on there. And then we have this giant amount of planets. And this is an outdated graph because I'm lazy, but it still like proves my point. We have all of these planets between the sizes of Earth and Neptune, which we do not have in our solar system. We don't have a planet there. There's the Earth and Neptune. And all of these planets, for the most part, are orbiting within Mercury's orbit. So We don't have a planet like this, and we're going to name it a super Earth or a mini Neptune, depending on how large its atmosphere is, if we can detect an atmosphere. I'm going to call them super Earth, and it's this population that my research focuses on. Okay, so the last thing that we discovered from Kepler that was very weird is that we found a lot of very compact systems. So we have a lot of these planets that are near their stars, but it's not just like each system has one planet near its star. Each system has numerous planets near its star. And so this was one of the first compact systems that we were able to characterize. It's called Kepler 11 because it's the 11th system that Kepler found. And this system has 4 planets orbiting within Mercury's orbit and then 1 like right outside, if we were to put it to scale of our solar system. This is not a unique thing. Most of the systems that we have found with Kepler are more compact than our solar system. I want to say all of them, but I have not looked at every single system because it's like 1,000, so just go with most. All right, so we have these weird things. And so we have to figure out, okay, so we have our solar system. We made a theory about it, that was cool. But then we have all these other solar systems that are so vastly different than our solar system. And we have to ask the question, all right, how did this happen then? Like, is our solar system weird? Or is there just like a wide spectrum of different conditions that are going on and our solar system is plotted somewhere on there, maybe like near the edge because it's like very strange. So there are 2 different ways to solve this, sort of. One, which I've called idea A, is just that planets formed this way. We were just wrong about planet formation. And by that I mean we don't have a complete story. We didn't have enough data, so we couldn't say, all right, well, planets form along this whole range of conditions, and here's our solar system, and here are other systems, and everything's dandy like that. The other idea is that planets formed where we think they did, using our nebular theory, and then they afterwards moved. We call that migration. And so we're going to talk about each of these in like a variety of different ways because my research focuses on trying to figure out which one of these is most likely to be true, either in the population or in specific systems. Okay, so idea A, planets form this way. So this differs greatly from our original concept of planetary formation, right? We had this idea that we would only have gas planets if they formed fast enough before our star is fusing hydrogen and before it removes the gas from this protoplanetary disk. So we had that idea, but that doesn't seem to be right. And we also had this idea that we would have planets sorted neatly, from leaving from their stars toward the outer edges of their systems of terrestrial planets, then gas planets, and then icy bodies that are small. We don't see that in other systems, we just don't. So something about this has to be corrected. In addition, to get our planets so close to their star and to get these super Earths, we're going to need a lot more material there than we think our solar system had. So for our estimates, just for numbers, currently we need about 2 to 10 times as much material. Now, this isn't that like unheard of. When we get mass estimates of different protoplanetary disks, we can see that there are different densities of mass. And so if you have the mass that's being moved itself from the outer edges, or the middle edges, I suppose, of the protoplanetary disk, then you can accomplish this. Also, please enjoy this glorious data of protoplanetary systems, because I feel that most people don't get to see them. And they're very nice, because people dedicate their lives to getting nice pictures. All right, idea B, which I initially had called like idea 1, but my fiance was like, that's weird, because they're equal. Okay, so idea B is that the planets formed where we think they formed, further out from their hosts, from their stars, and then migrated inwards. So this process of migration is not a new concept, and it's a fairly robust idea, that you have planets that are in a disk, and this disk is composed of gas and dust, and what we call planetesimals, which are like asteroid-sized bodies that hope to be planets one day. And so as these planets are interacting with their disk, they're going to be exchanging torque with the disk. Sorry, the disk is going to be applying torque, and that is going to exchange angular momentum. And whether the planet is gaining angular momentum or losing angular momentum is going to cause it to move outwards or inwards, respectively. So this is a concept that we've applied to, say, moons in our solar system before we had exoplanets. So when we initially were finding these giant planets close to their stars, we were just like, oh, they just migrated. And then things just kind of got a little squishy because it's like, okay, well, did all of them migrate, or just like half of them, or what portion of them had to have migrated versus could have formed there? So if we assume that migration is going to be applied to all the systems, might as well. That's what the community started doing. They're just like, all right, we'll just say it's migration, wave our hands, we're all good. There are a couple consequences of migration that we can test. So if we have migration applied to basically all systems, we're going to end up with close-up in planets, which we have. So here's just another version of the radius versus orbital period plot that I had showed you with the different populations that we found. And here I've marked Mercury's orbit and then Earth's orbit, just as vertical lines. So we have a ton of planets within 10 days. So we definitely have close-in planets. The next thing that migration predicts is that we're going to have compact systems. And like I mentioned, most of the systems that we have are very compact in comparison to our solar system. So like, cool, that's awesome. The last thing that migration predicts, though, is what's known as orbital resonances. And so my research, a lot of it is, are there orbital resonances that were caused by this migration? So for background, generic across the universe, the word resonance means a phenomenon in which an oscillating system or an external force is going to drive another system to oscillate with a greater amplitude at specific frequencies. So this term is used very frequently throughout, say, vibrational systems. So you can have a resonant spring, you can have a resonant frequency. There's this whole like concept of shattering glass with a high-pitched voice thing. One of my favorite examples is the Tacoma Narrows Bridge, which I have a nice GIF of here. This was a little weird because the bridge had a natural flutter that the wind was just driving, but the bridge was physically moving this way. This was a while ago. And so people now are more aware, civil engineers are more aware that they should not let bridges do this. So when we're talking about planets, we are not talking about bridges, although that'd be cool. We're going to compare the frequencies of their orbital frequencies or their orbital periods, because I prefer talking about it takes 10 days instead of like they do 10 revolutions in a year or whatever. If a planetary system is in orbital resonance, that means that its orbital periods between the two bodies, if you take the ratio, it can be reduced to a ratio of small numbers, which is like a really weird thing. So I have an example. So Jupiter has some dope moons that are doing some really cool things. But what's useful for me is three of them are in an orbital resonance with each other. And so every time that Ganymede goes around Jupiter 4 times, Europa has gone around twice, and Io has gone around once. So this is cool, and we're going to use this to try to figure out whether these planets are migrating or whether they formed, whether we observe them, or like some combination of all of that. But before we get into that, a quick cool thing. Orbital resonances are fantastic, and I wish that they taught them at normal curriculum because I think they are super amazing, and I am a nerd, so that makes sense. But if you have bodies that are in an orbital resonance, they can maintain like their orbits or a orbital configuration that is, without the resonance, very unstable. That would lead to things colliding, things being ejected, things just going haywire. So an example of this is our planet Jupiter, which is a pretty cool planet, has asteroids that are sharing its orbit. And these asteroids, whether they are leading Jupiter or trailing Jupiter, are called the Trojans and the Greeks. Or more generically, if you have any asteroid that is in the orbit of a planet, we just now call it a Trojan asteroid because we get lazy. But you can see here these like green clumps of bodies are in fairly stable orbits with Jupiter. All right, so this is a long-lived thing. This has been going on for over 4 billion years. It's not just going to suddenly upend. But in addition to these 2 sets of asteroids, we have another set that's in like this pinky reddish color thing. I don't know what color that is, called the Hildas. And these are also in an orbital resonance, but as you can see, they look a lot, to your eyeballs, they look a lot more unstable. They definitely look like something's going to happen there, and they're just going to interact, and they're going to go somewhere that's not in orbit. And that's not going to happen. They're going to stay here forever until something else is going to bother them. Like if, I don't know, Saturn were to go haywire, then they might move. But for now, they're just going to stay here. This can get even more exciting than asteroids. So we can have planets in our solar system that are in orbital resonance, and their orbits are going to cross. So Pluto crosses Neptune's orbit, which is kind of fun because when it used to be classified as a planet, it was sometimes like the 8th planet, not the 9th. It was sometimes closer to the sun than Neptune, which I just think is fantastic. But anyways, Pluto and Neptune are in a 2 to 3 orbital resonance. And so even though Pluto crosses Neptune's orbit, because of this resonance, they will never be at that point at the same time. This is long-term stable and will not change until some other gravitational force is going to move them. They will forever stay like this, never meeting, which is good for us, I guess, unless you want to see a really fantastic collision, which would be cool. Okay, so orbital resonances are dope. Now, how do we know that planets are in resonance? So I told you that this resonance is defined by the ratio of the orbital periods, but that's just kind of like a hint that they could be in resonance. There are a lot of things that can change the period of a planet, the orbital period of a planet. That doesn't necessarily mean that it's going to change the resonance. So what we're going to look at is known as the resonant angle. And these are GIFs, but I'm not going to start them yet. On the left-hand side, we're going to have 2 planets that are going to be orbiting as they feel like it. And specifically, they're going to be in a 2 to 1 resonance. So every time that the outer planet's going to go around once, the inner planet will go around twice. And then on the right-hand side, we're going to plot the angle at which they are having their closest approach, or their conjunction. All right, so right now they're on the line, they're conjuncting on the line, but you're going to see that they're going to sometimes conjunct early and late. All right, let's hope that these are synced up, because I spent like 15 minutes getting them synced because past me decided they didn't need to be one GIF, and that was a foolish person. Past me was foolish. Sweet. Okay, they're in sync. Okay, so as the planets are orbiting around, I've colored them white when they're at their closest approach with one another. Okay, and we are just plotting that angle of their closest approach, and it's going to form a very nice sine curve, or cosine curve, whatever floats your boat. So it's this sine curve that we are looking for when we say that 2 bodies are in resonance, and later on we can get 3 and 4 and 5, because that's cool. We're looking for this sine curve. Okay, so also this GIF took me like a very long time to make, so that's cool. Okay, so this resonant angle is going to be a combination of the different orbital angles from the different bodies. And so what I showed you back then was a 2-body angle, and here's the math of it. You don't need to know the math of it. I don't know why I put it in here, but I did. But what's important is I have included simulations from my own work of 2 different systems, one that is in resonance, one that's not in resonance. So we'll talk about the one that's in resonance first. It's on the bottom. When systems, when the angle is oscillating, we say that it's librating for jargon reasons. And so what's happening in this bottom subplot is that in the very beginning, the planets are not in resonance, and then they lock into resonance. Now, what's interesting in this specific example that for whatever reason past me decided to use, there are 3 other bodies in this system. This is a 5-planet system that I modeled. And so there is a part halfway through where another planet locks into resonance, and it changes the amplitude of this resonant angle. That is not important. I just wanted to say that because people are like, but it gets smaller. What does it mean? It doesn't mean anything. Now, the top part is when the planets are not in resonance. So we oftentimes use a pendulum to explain what we mean by resonance. And so if you imagine a pendulum, oh, I have a thing. I have a Haumea necklace. Haumea is like the dopest dwarf planet, and for some reason it's right next to your head. So we have a pendulum that's going to be swinging, all right? This is similar to, oh, I'm so impressed with my pendulum skills. This is similar to a librating angle, all right? It's oscillating in some degree. Now, if we give it enough energy, oh, I don't know if I can do this. If we give it enough energy, there we go. It's going to start, I don't know if you can actually see it, I'll slow down. Okay, yeah. Thank you for Caleb for nodding. Okay, so it's going to circulate, and that's going to be different than oscillation. So when a resonant angle is not librating, we say that it's circulating. Now, this doesn't look like circulation, right? This looks like random points that I've just plotted and put a line through them. And that's just because we have to compare the frequency of its circulation to the frequency of sampling, and it's going to lead to weird things. But sometimes you can get it to be like nicely plotted, and you can just watch it circulate through all the values. Okay, we're going to move on so that I don't just like use a ton of time talking about what's cool. Now, the whole point of this is, all right, so planetary migration predicts then that a lot of our planets would be in resonance. So what I've plotted here is another histogram of the y-axis is planet pairs, and the x-axis is their ratio of orbital periods. All right. So, and I've plotted as like dashed vertical lines really common orbital resonances. Okay. So if this question like, are there planets that are frequently in resonance? And the answer is not really. We kind of have like, we have some planets near this 3 to 2 here. 11 pairs out of 4,000 planets. Like, okay, cool. We have some near this 5 to 3, again, like 11 planet pairs out of 4,000 planets. Like, okay, there are some in resonance, but like not most of them. So this kind of like puts like a fairly sizable hole in the thought that most planets are migrating. But some of them are migrating. So we're going to focus on the some that are in resonance, and we're going to see then if those that are in resonance have to have migrated. We're just going to keep testing this from like every possible angle. Okay. So what is a lot easier to identify is a multi-body resonance. So we call that a resonance chain, and this is just 3 to like 7 planets that are in resonance with one another. So a really common example of this, which is like a really awesome system, is the TRAPPIST-1 system. And I've labeled here just the period ratios of the planets. But I can tell you that these planets are all in a singular resonance chain. So they are all...
There is a reminder for Joey.
Sorry. They are all exchanging angular and linear momentum with each other, which is a cool thing that resonances let you do. Okay, so what we're going to do is we're going to study these resonant chains because they are kind of examples of what would happen if all planets were forced to migrate, right? Because if you have planets that are just evenly distributed or like randomly distributed, and you force just one to migrate, as soon as it locks into a resonance, that's going to keep migrating until it locks another planet into resonance, and it's going to keep migrating until you lock another planet into resonance. So these resonance chains were kind of like our last, like the community's last hold on to, but they must migrate. So we're going to test that. So if resonance chains come out of this theory of planetary migration, we're just going to like turn that on its head and be like, all right, that's cool, but do they have to be formed from migration, right? Or can they be formed from other things? So that was like half our background. Yeah, we're going to get into research now. So we're going to make a step 0 of this plan of, all right, can we test how resonance chains form? And the step 0 is going to be find systems that we think have resonance chains and verify that they do. I make it as a step 0 because this took like years and I'm still doing it and other people are still doing it. So here is a graph of all of the resonant chains that we know of / suspect, but cannot yet, don't have enough data to confirm. I made this like 3 years ago, and since we've had one more system, and that is K2138, which I can tell you will be published soon via me as being in resonance. So we have a lot of planets, but we don't have a lot of resonant chains. So that makes my work easy, at least, because then I can test all of them. All right, so just an example, also because the system's like my child, I got to edit Wikipedia, which was the coolest part of my career. Like that was like 3 years ago, and it's just downhill from there. But so Kepler 80 has now 6 planets, and as a fun thing, planets are named like B, C, D, E based on their order of discovery, not necessarily any other logical reason. So that leads to Kepler 80's planets being F, D, E, B, C, G, which is abnormal and very fun to talk about at conferences. So all of these planets, we call them super Earths. They're like 1 to 7 Earth masses-ish. The planet G I just got a mass estimate on it, actually probably smaller. It's about Mars size, which is cool. And the outermost planet has an orbital period of 15 days. So this is a very compact system. Now, back when I first was studying the system to confirm its resonance chain, which by the way was the first confirmed resonance chain in exoplanetary science, which I just love to toot my own horn there. So I made this like really cool GIF, which is now not so cool because I have more computing skills now. But what I have done is I have graphed the planets moving in circles, which doesn't look like it from here. I promise they are moving in circles. And I've stopped it whenever the two outer planets are conjuncting. So that's red and green. And if you're colorblind, I apologize. I was not aware of color blindness when I was in undergrad. So yeah, sorry. Anyways, and then I have rotated the frame so that they're conjuncting in the same point of reference for us every single time. And you can see then that when they conjunct, that the blue planet and the purple planet are going to be in about the exact same place. So another way to look at a resonance chain is this repeated geometric configuration. Now, innermost planet F is having a party. It's just doing its own thing, and it does not look logical at all. And that's just because it's not part of this chain. So this is what happens when you have a chain versus not a chain. You just do your own thing, and you follow your friends. Okay, so we've confirmed systems. We have 4 resonance chains that are confirmed, and 2 more that are suspected based on their period ratios, but we don't have enough data to absolutely say one way or another. So we'll just say they're suspected. So the next step is we're going to fake form these systems. We're going to simulate each of the systems, and we're going to form the planets where we observe them and see if they lock into resonance. And we're going to form the planets in like a separate suite of simulations way far out. We're going to start with the innermost one at 1 AU, which is the distance between Earth and the Sun. We're going to spread the other planets out, and we're going to force them all to migrate. And we're going to compare the results of all of that. Okay, so this is what I mean by we're going to start planets out pretty far away and make them move, and we're going to start them where we observe them. So this is Kepler-80 just as an example. So you can see that outermost planet in Kepler-80, we started at like 1,500 days, which is pretty far away. And then it moved in because we're just going to force it to do that. And then when we form the planets where we observe them, we are going to apply a tiny amount of torque to them because these planets still would have been in a disk. Even if they formed where they are, they still would have been exchanging angular momentum with their surroundings. So they're still going to do like a tiny bit of migration, and you can see that here, but not like this long, large scale from the edges towards the center migration. Okay, so step 2 is we're going to look for these resonances, right? This is useless if we just like simulate planets and they don't go into resonance. We're like, oh, that doesn't tell us anything. Okay, so we're going to verify that everything is in resonance. And so I've included that like blue and white plot from the beginning. And then up top here, I've just included actual data from our simulation. So this is another system in Kepler-80. We're just going to look at all different ones. And you can see here that in the beginning of the simulation, the planets are not in resonance, right? These points here on these angles are scattered randomly, and then they lock into resonance and they stay there. This angle will be lagrating, it will be bound, and it will not, for the most part, change. So this is what we look for in all of our thousands of simulations to confirm that our simulations did start the planets out of resonance, because it's not helpful if we start them in resonance, and then lock them into resonance, and that stayed there for hundreds of millions of years, because we need it to be long-term stable for us to have observed it. Okay, step 3. We're going to now that we've confirmed, we have simulations that we forced to migrate, simulations that we form the planets where they are observed, and we have confirmed that all of them are in resonance. Great job, me. So we're going to then compare different results. Or if not all of them are in resonance, we're going to compare which one was more likely, which formation pathway was more likely to lead to resonance. So here's an example of another system. And what we're plotting here is on the left, we're still plotting migration. On the right, we're still plotting in situ formation. We have 3 different resonant angles. The top one is a 3-body angle, and then the second and third are 2-body angles. Then we have the orbital periods again. Okay, so for this specific example, you can see that like A, the planets migrated, and B, they're in resonance. We have a couple other things that we can constrain. You can see that the amplitudes of libration are very different between these two, right? Like that second angle on migration is like a super fat boy. And you can also see that the center of libration is going to be changing, sort of, sometimes, depending on the simulation. So we're going to use all this information, and what's also not plotted on here is the planet's eccentricity. So we're going to use that also, because some of these planets actually have eccentricity constraints. As a side note, most of them don't, because it's very hard to uncover an eccentricity from the transit method, unless they're like highly eccentric. Then we're like, oh yes, there we go, eccentricity. But usually it's like less than 0.1, and that's all we get, which is not super helpful. Okay, so we've done all this. We have made fake systems based on real systems. We have confirmed whether they are or are not in resonance and what conditions are going to lead to that resonance. And so now we're going to try to answer the question, if resonance chains, they are, actually not if, they are a logical consequence of planetary migration, right? But must the systems that we found be formed with migration? And the answer is nope. We're just gonna keep testing this. Okay, so, all right, so we got this point now that what people considered, what the community considered to be absolute proof of migration is no longer absolute proof of migration. Like it's a good suggestion of migration, but if we can form them via other ways, that doesn't mean that they formed via migration. So that being said, as you saw, we only had like 6 systems. So once we find more systems, which I'm actively trying my best to do, and like hiring people, then we can have more systems to test and everything like that. Okay, so we're gonna switch gears a little bit and be like, all right, well, resonances didn't really work out. They were thought to have worked out, but we've verified that they're not. So we're going to try to test other things to see if in situ formation is going to work. So when we look at all of the different planetary systems that we have, we're going to ignore the solar system for reasons. When we look at all of the planetary systems we have, minus solar system, we see a very wide range of different systems. We have a lot of systems, as I said, that are compact. Great. We also have systems that are compact with like one really like wide, far away planet. Like, okay, why? We have systems that are flat and what is known as dynamically cold. They are not like mutually inclined. They're not like super eccentric orbits. They're just kind of chilling there. Very similar to our solar system. That's cool. But we also have systems that went haywire, that have really random orientations of their orbits. Some planets are like on their sides, like things just went messy. And whatever like formation history we give them, whatever our theory is for how planets are forming as a population, has to satisfy this whole wide range of diversity. It also has to satisfy not just the diversity of the systems and their orbits, but also the planets themselves. We have some really weird systems out there that are only tiny Earth-sized planets, that are like only Jupiters, that are like a Jupiter next to the star, then like a terrestrial planet, and then like a super Earth, and then like another super Earth. Like we have some really weird things going on. And so whatever we do is going to have to explain all of this. So there have already been studies trying to explain this all with migration. And so what I decided to do was try to explain it then with just in situ formation, just having the planets form where we observe them. Okay, so this was what we started with the nebular theory, that we think that our solar system formed out of this collapsing cloud, gas and dust, and it led to our very nice, really calm solar system of nicely sorted planets. That's just really great. But we're pretty sure that this is incomplete. Okay, so we're going to have to change it. Now, another way to look from like this cool little diagram, so we're going to focus on the last stage of planet formation. Okay, so when you have your gas around, you are now a protoplanetary disk, apparently. Okay, when the protoplanetary disk still has gas within it, this gas is going to be damping a lot of interactions. So it's going to cause things to essentially not smash into each other. And the very last stage of formation is things smashing into each other. It's known as the giant impact phase. It's how we got our moon. Our moon's pretty cool. I bet you can all agree on that. So we had this nice story, and like we're only looking here at what I've noted as the inner disk, And so that would be what our terrestrial planets came from. Within what's known as the ice line. So we're ignoring all the gas giants for now. We're just going to pretend they're not there. So looking at the terrestrial planets, the giant impact phase did not occur until after all of the gas was gone. So the gas was making sure things didn't smash into each other, and then once the gas was gone, things smashed into each other, and we end up with very small terrestrial bodies without appreciable atmospheres, right? Like we have like a cool atmosphere, but it's really puny and insignificant compared to most atmospheres. Insignificant in terms of like mass. It's obviously very significant for life. But so we're gonna move things up a bit. We're gonna shake them up, as apparently what Passme typed. And we're just going to adjust this slightly. So for having these planets form in situ, the one requirement is there needs to be more material, more mass in the inner disk. So there are many ways for this mass to occur. It can occur naturally, it can be delivered. You can have like really cool like wakes in the disk that's going to like move mass around all fancy like. However it happens, we're just going to start out with there's now more mass in the inner disk. All right, and we're going to put that mass specifically in the dust part, not the gas part, the dust part. And we're going to call it solids. Now, with enough mass here, the gas disk is no longer sufficient to damp out the dynamics and ensure that things don't smash into each other. So we're going to have our giant impact stage while there is still some gas around. This is going to lead to a variety of things, but one of the main ones being that we can now form super Earths and mini Neptunes. We can now form planets that are large enough that they can accrete a small atmosphere before the gas disk is removed. So this is our new concept, and to put it in scope of the like other cool like 3-step diagram thing, we are just going to add in a tiny little phase here that is that because of the higher amount of solids in the inner disk, we can now have this giant impact phase earlier on in terms of like the star's formation and it removing the gas. So we're going to call this the residual gas era, and it's during this that we are going to be forming these super Earths. This is going to lead to a couple interesting dynamical things. Now that we have larger and more massive planets that are going to be closer to their star, that we're going to have stronger gravitational interactions between the planets, which is going to lead to a couple ejections and collisions, but for the most part, it's just going to lead to some inclined and eccentric orbits, which we need because not all of the systems we found are nice and flat and calm and cool and collected like our solar system. They're just wild. So this is our theory, but we have to test this theory, right? I can just tell you all day long, like, oh yes, we have more solids, we get the planets we need, but we need to actually test this, or else it's not science. So the question that I have is, without migration, if we form planets in situ, can we reach this diversity of systems and this diversity of planets? So we're going to do steps again. I'm a very step person. My brain likes steps. So step one, we're going to create a bunch of fake systems made of planetesimals, which as a reminder are like rocky bodies that hope to be planets one day. And we're going to keep them in a small amount of gas. At this point in like this protoplanetary disk's evolution, the star has started fusing hydrogen, has started having a solar wind, and the gas is starting to be removed. But there's still some gas. We need that gas. All right. And then we're just going to drop planetesimals in some gas. Then we're going to move time forward. For example, 1 million years. We know that protoplanetary disks persist for about like 1 million to like 10-ish million years. So like planetary formation is happening within there. So 1 million years is pretty realistic. And after this 1 million years, we're just going to take away the gas and thoroughly let things smash into each other. There's going to be some smashing. The giant impact stage is going to be occurring during the gas, but the gas is still going to be doing some kind of dampening. So once it's gone, then we can have that nice dynamical evolution that's going to lead to a more eccentric and inclined orbits and some like weird planet mixing where you can get your planets to be not in the nice order of terrestrial and gas than icy. Okay. And then step 4, which is a very crucial step for science, we're going to observe these systems. Now, what we see in our systems all had to be observed. And because we're, by the way, focusing on just Kepler systems, I don't know if I said that. Maybe I don't think it did. We're just focusing on Kepler systems. So all of these systems had to be observed by Kepler, which means that the planets have to cross between the line of sight of us and their star, which is not all planets. We know that for sure. However, we don't know like anything beyond that, except that we don't have the complete story. We don't know what the complete story is though. So what we're going to do is after forming all these planets, we're going to have some population of planets, but it's going to be different than the population that Kepler would have observed. So we're going to force a tiny algorithm that is not named Kepler, but is just named planet algorithm, that is going to look at our systems and then determine which planets would have been detected in every single system that we simulate. Okay, so here are our results. Also histograms. Histograms are dope. So what you're looking at here in the top left-hand corner is the distribution of the period ratios, which I showed you in context of the orbital resonances. But that in conjunction to the graph next to it, which is titled Hill spacing, are different descriptions of how compact a system is. All right, that's all you need to know for now. In the bottom left-hand corner, we have this nice log 10 of psi, and that is just a description of the inclination and eccentricities of the different planets that we can recover from transits, because as I mentioned, it's very challenging to get eccentricities from transits. And then the bottom right-hand corner is the number of transiting planets. Now, I can tell you from having studied these and read too many papers, that this is a fantastic fit. I understand that it doesn't necessarily look like that, but this is a fantastic fit and one of the best in all of the literature. All right, so we were able to find that our in situ formation with this residual gas stage led to, at least in this case, the orbital diversity that we have in different systems. I also want to toot my own horn again and say that the number of transiting planets, the histogram, was the best that's ever been published for a model to match observations. Typically, it's very challenging to get that giant peak of just one, but still have a tail that leads out to 8 planets. And most people are like, there are 2 ways to form planets then, and we're just going to add them together. And so this was the first and so far still only thing study that was we're not going to add things together. We're just going to do one thing and it's going to form a histogram. Okay. That was really cool. Now, in addition to diversity we see in the orbits, we still have a diversity of planets. And so what I've plotted here on the x-axis is mass and y-axis is radius in Earth units. And you can see here, there's just a giant scattering. Now, without context, you're like, all right, this is cool, I guess. It's a graph, colored, amazing. But there were a couple pretty significant problems in exoplanetary science that we couldn't resolve. One of them was that if you find the mass of a planet via radial velocities, which results in the planet tugging around its star, and we can observe that star move a little bit in its spectrum. Those masses were different than if we were to detect the mass of the planet gravitationally through changes in planets' transits. Those were different, and that was not okay. It was a really weird problem. People were like, I don't know what's happening. So specifically, if you were to graph the planets in one group and the planets in another group and their mass and radii, they would have different lines, and that was just a weird thing. So we found out that if you have differing amounts of masses, so we've already increased the mass in the inner protoplanetary disk, but if you have different amounts throughout different disks, which is logically acceptable because the universe isn't just going to be like, no, only 50. It's going to be a range. Then we can recover these different mass radius relationships that people were finding depending on how they were measuring the masses of the planets. So we found that this method can also explain the diversity of planets, actual planets, not just their orbits and everything like this, but their compositions and their sizes and their masses and how they are distributed throughout the system, which I don't have a graph for you right now, but know that they were distributed as we observed them. So this was pretty fantastic. Now we're going to bring it back one last step to my favorite thing, which is orbital resonances. And it's okay, well, you made all these planets and that's cool. And you satisfied some things that you observed and also cool. But you started out with resonances. And so if you're forming things in situ, you still have to have some resonances because we have observed some resonances. So the cool thing about our simulations and our theory is that we came up with the same percentages of resonant chains as we observe, like the exact same, which is not that, it's not as fantastic as it might sound if you consider the fact that we only know of 4 with like 2 potential ones. So we uncovered 4 resonant chains. And so what I've just plotted here is the different resonant angles of different systems, and I've marked the runs red if a resonant angle is vibrating. So you can just see it do its thing. Okay, so that was all my science, which I guess was faster than I had planned, and I apologize for that. We can talk about my life in a second. So resonance chains can be very useful, and they can be used to constrain an individual system's formation history. But there's a giant but here, is that they cannot be used to constrain a population's formation history. We can't just say that all resonant chains mean that all of the systems migrated or all of them formed in situ. What I'm currently working on now is using the amplitudes of the libration and the centers of the libration to uncover the likelihood of which pathway they formed. This can only be done currently on 2 systems, so it's not that, or I guess 3 once I published K2138, but it's not that like phenomenal in terms of numbers yet. It takes time. Okay, and then the last thing is that if we look at all of the different planets that we have, we can explain it by just modifying our initial nebular theory. Right? We don't have to say like, okay, all of the planets must have migrated, even though our planets in the solar system didn't like super migrate. They migrated a little, but then they went back. And so it's like this weird thing. So we can do this. And this is a fantastic thing because it means that we no longer have to constrain ourselves and our minds to just one idea, right? It's also maybe frustrating because maybe you wanted that one answer, but science doesn't just give you the answer you want. So we now more understand planet formation, and as we have more missions that are still collecting data, such as TESS, or will be launching soon, hopefully, James Webb, then we'll be able to go back to this idea, and we can do new studies once we have more data, and that will just continue forever, probably. Yeah, that was my science. And so, like, nobody interrupted me. I know I did go fast. I tried not to, but I did. Before I move on talking about, like, my life, because I was asked to discuss that, does anyone have questions on science? I realize I should have said on my science, but also any science. I can try.
So I'm actually, sorry, excuse me. I'm actually doing research in exoplanets, like undergraduate research here at BSU. So we usually use the transit method as well. My question is, how are you able to tell the like the orbits of the planets based on the transit method? Exactly.
Right.
Like the periodicity.
Right.
How they
So the one, or I guess there are two, let me start over. To constrain an orbit, there we go, we'll just start there. You need the orbital period of the planet, or you can use the semi-major axis, which is a description of how far away the planet is from its host. So we can get that from the transit method because we can just watch the dips and measure the time between the different dips as the planet goes in front of its star. And so it's pretty easy because most of our planets have very short orbital periods. And so we can just observe it for like 10 days and watch 3 transits if it's a 3-day like orbital period. And then we can be like, yes, that's great. So there are really fun ways to do that. Usually you don't like use your eyeballs, use algorithms. And so the algorithm will be testing a variety of orbital periods, and you start it somewhere. So with your eyes, you can be like, it looks like 10-ish, I don't know. And the algorithm is going to take the data and do what's called folding it. So it's going to take each, say, 3-day section of data, and it's going to just plot it on top of each other. And as you do that more, you recover more constrained transit depth, transit curve. And so if you got your period wrong, though, you're not going to get that. You're just going to get random data because it's going to be random dips that were plotted on top of each other. So we can get the orbital period out from that, which is fantastic because that's kind of like maybe one of the most important things. The second thing that you can get from this is the inclination of the orbit, or the orientation of its tilt with respect to our line of sight. And so if it is edge on, we say that's an inclination of 90 degrees. And if it's face on, that would be 0 degrees, but we can't see planets cross in front of the star if they're just going to be from our line of sight orbiting around the star.
That'd be radial velocity, right? That
Yes.
they use? All right.
Yeah, so we can get the inclination from transits, but usually it's like 89 to 90 degrees. Like it's a very small range usually. And there are other factors that can lead to you mismeasuring the inclination, but they're rarer. The other thing that we can get sometimes is the eccentricity. And so if you have your transit curve, and we're going to say it's a perfect curve, not like real data curve, it's going to be a nice like trapezoid. The time when the planet is entering the star's like surface area and the time when the planet is exiting the star's surface area are known as the ingress and egress. And so they're going to be like the diagonal lines in your transit curve. And if those are vastly different, then we know that there is a change in velocity occurring of actual planet, which is going to be caused by an eccentric orbit. So it's a really weird thing. So what we oftentimes do when we're trying to recover planetary orbits, aside from the things that we can directly measure, like the period and the planet's radius, is we're going to model the system. So we're going to assume some eccentricity. We're going to model it. We're going to come up with a fake light curve, fake data, and we're going to just compare that. So that's known as forward modeling, and that's most of exoplanetary science. And it's kind of backwards, but we can't, for the most part, do like experiments.
Right,
So
right.
yeah. So the other three things that are important, we have 2 more orbital angles. So we have the inclination, which is nice. If you have an eccentric orbit, we have the orientation of that, which if we have, if the planet is eccentric, we can sort of uncover that. But if the planet is not very eccentric, if its eccentricity is less than 0.1, we just have no idea what that is. So we usually assign it a random value. We have one more orientation. So if we have, let's see, we have this one and this one, and we have this one. There we go. Science is hard. And that one we also can't constrain at all. So we just assume it's 0, which is fun. And then the last thing is that you need timing information. All right, so you have your orbit, it's nicely drawn out, but you need to know where your planet is with respect to our clocks. And so that we typically just use the time of the midpoint of the transit, and we just report that.
Oh, okay, that makes sense. Yeah.
And so that way, if there are multiple planets, we then know that like, all right, well, this one passed, and then like, 5 hours later, this one passed. And so we can then figure out how they're oriented with respect to one another.
I think that actually makes a lot of sense because my main research is in candidate exoplanets, which we're not entirely sure are there. In the midpoint, like the range in which the uncertainty for the midpoint is just, like on a span of like 2 hours or so.
Yep.
Like I had to stay up all night just to get my data.
Yep.
It's crazy.
Yeah. I will say it's one of those reasons like that I am a pure theorist. I do not observe whatsoever. I don't have the patience. Like I just just give me data and I will use it and I will simulate things. But yeah.
Personally, I see it as an opportunity to get some homework done, like without distractions.
That's fair.
Well, with a distraction, but
yeah, that's fair.
Yeah.
Oh, thank you, Megan. My students, last year I taught at 8 in the morning and they had to deal with my enthusiasm at 8 in the morning and I had to be like, I'm so sorry, but this will not stop. And it only gets worse when we get to planets. So I teach mostly intro to astronomy. But okay. Do you guys have any more science questions? I can also answer, one of my fields is astrobiology, and so I can do that.
I had one question.
What's up?
Do these models of formation of planetary systems, do they tell us about the composition of the planets?
So no and yes. So we can track, if we assume a composition of gas, we can track the size of the planet's atmosphere, and that's essentially it. My next, I just submitted a proposal for tracking the composition of these planets. It's just really computationally intensive. And so you need to be essentially at a university with the coolest supercomputer, and then you have to somehow get time on it. So for context, these simulations of just the modeling of a dissipated gas disk and then afterwards took 3 weeks to run. And tracking compositions takes around 5 weeks with 5 times the amount of RAM of memory. And so, so I need to secure 200 gigabyte nodes of just RAM. And that's very challenging to do, especially as a grad student, because they're you don't matter. So the answer is technically, yes, we can do it. And we're getting to the point where it's computationally feasible, but it has not been done yet.
Okay, thank you.
Mm-hmm.
So in your simulations, you're tracking gravitational interactions. And then when you say you're stripping away the gas, it sounds like you're not necessarily simulating sort of solar impact or hydrodynamics within the gas, or are you doing that? And then when you say you strip away the gas, you're just sort of blanket removing it and saying the solar wind is turned on now and blown the rest of the gas away. How are you sort of interacting the sun with your gravitational dynamics?
Right. So we're not.
Yeah. Okay. That's what I figured.
Yep. So everything in here is just a point source, and we're just tracking gravity, and then we're modeling the gas as just a damping force. So the gas isn't even modeled.
Okay.
It's just a damping force. And you are right that after the 1 million years, we just kind of turn it off.
So just like a basic, so I'm also teaching mechanics this semester. So you're just doing a basic, V squared damping parameter of this a certain density gas, and I got this big rock moving through it. So you're tracking how the planets are moving relative to one another, and then just damping them like a velocity damping.
Yep.
Cool.
Yep. Which is kind of when you boil it down to that, it's well, that's not how it works. But we don't have the resources to make it more realistic.
Sure.
Yeah.
No, but it makes
especially
a lot of sense.
because what does really bother me though is that these planets are oftentimes close enough to their star that the tidal interactions from the star would be interacting in some way. And in addition, the radiation from the star would be affecting their atmospheres. But we just can't model that yet. I mean, we can model it, but just isolated.
Yeah, so that was another one of my questions, right? So the way that we don't strip atmospheres with the solar wind is that we have magnetic fields.
Yep.
And so are you making some sort of assumption about the magnetic fields of your planets? And is that
Right.
part of your model?
So it's not. You can also counteract that if you have a massive enough planet that's far enough away. And
Yeah.
so we just don't, this is the fun part, we don't model atmospheres that are within a certain distance to the star and mass.
Okay, that makes sense. Sure.
So that mass radius diagram was ignoring the closest planets. Yeah. I have these dreams that one day I will own a supercomputer. That's what I'm going to do when I get rich. And I will do science. Yeah, that's apparently what my dreams are. I'm just going to become rich and have a supercomputer and just continue to do work. All right, well, so I guess I will move on to talking about my life. If you have any other science questions, feel free to ask, put them in the chat. And this includes if I say something randomly later on and it triggers something, you're oh, I wanted to know about that thing. Feel free to ask. I don't really care about linear timelines. Okay. So I was asked to talk about my average workday, which is a very challenging thing as a grad student in academia. And so I have separated it into different chunks and given this nice title that my average workday is 5 to 15 hours long, which is a very wide range. And so that just depends on different deadlines I have, which are usually fake deadlines. It's something I feel that people don't talk enough about in academia, is that you rarely have actual deadlines. You just like make some up for yourself and you're like, I will publish this in 1 month. And then you're like, the deadline's coming. Okay, so most of my time, not even most now, I don't know, a quarter, a third of my time is spent doing research. As I mentioned, all of my research is theory and it is all based on coding. So I'm now a hashtag hackerman, and I can code in 8 different languages, which is a really fun thing to tell people. Just in general, like you can be like, I can code in 8 different languages, and they're like, that doesn't mean much or means a lot. I don't know. But most of my coding is in Python and a language known as IDL, which is a little bit old now, but it's kind of like the astronomer's language from the 90s. Yeah, that's how cool we are. I also use MATLAB a lot, which is typically used by engineers and geodynamicists, and I use R for all my statistics because I do a lot of astrostatistics. So I do a lot of reading other people's work. Mostly this is reading the abstracts and being like, that's useless, and be like, that's useful. Or like if I'm reading outside of my tiny little field of exoplanetary dynamics, then I'll be like, oh, that's a really cool thing I can tell people about. What I feel that somebody should have told me when I was like in undergrad and I was like, I want to be an astronomer, is that academia requires a crap ton of writing, like so much writing, like nonstop writing. And so writing is a skill, and with time you get better at it and it becomes easier and you can write some fantastic things in a very short time, but a lot of my time I just spend writing. So for extras, I have collaborators that are across the globe. It's the cool thing about astronomy. Most people on the planet like astronomy, and so if you have astronomers across the world, then you can work with them. So I have a lot of different teleconferences, and it used to be in-person meetings for people at my institution, but now it's just a lot of Zoom. I advise students in research, and then I have different talks and conferences. Conferences are the best thing, by the way. If you're like currently doing astronomy research and you don't hate it, I recommend staying just for conferences, because astronomers decide that they have to get together to do research, and that's cool, but they should do it in the best vacation spots in the world. So I have been to Aspen, Colorado. People went skiing. I napped because I'm tired. I have been to Reykjavik, Iceland twice. I went to Hawaii twice. Like I have been to California, whole East Coast, middle of nowhere, like all over. And I've turned down so many international conferences because I don't have the 16 hours it takes to fly. Also, all of my conferences this summer were canceled, and I was going to go to Japan, and I was really bummed out. So a lot of my time is also conferences. I have to deal with, or used to have to deal with, the press. I'm now very like introverted and isolated, and so I don't really care if people know, like if lay people know about my research, and a lot of it is answering emails. So once you publish papers, you get emails from a variety of people that are like, I saw your paper and it's cool, or you get a lot of emails from more, we'll say, like senior academics that are like, I saw your paper and I wanted you to know that I wrote a paper. And that's like it. You're like, cool. I like your paper. I don't know what else to say to this. But anyways, a lot of emails. Now, the other thing I do is I teach a lot. And so I've been teaching for 2 years now, which is abnormal for a graduate student. So just say that out there, put that out there, which takes up currently like, I don't know, 70% of my time. It's ridiculous. It just kind of like, it's like a balloon that fills up until you have no free time. It's teaching. So this is just like normal teaching things, a lot of prep, doing the actual teaching, so much grading. I have a lot of freshmen, which means that I get a lot of emails. It's like, I haven't come to class yet, and I know we're on week 12, but can I have extra credit? And it's like, no, I don't want to give you extra credit if you're not going to come to class. Sorry, this is my life now. Okay, and the last thing that I spend about a third-ish of my time is on what I just generically labeled as service. So I do a lot of work on my institution's climate and their inclusion, like measurements, which is really challenging at a large institution. So I'm at Penn State, and the university itself, for the most part, just cares about football and money, and like nowhere in there is people's well-being. And so it's like a lot of weird uphill battles about like, no, we deserve to sleep 5 hours a night, things like that. When you get far enough in academia, I guess, so somewhere around grad school, postdoc, later on, you have to start peer reviewing papers or refereeing papers, which is basically that someone submits their paper to be published, and the journal is like, you are sort of expert, tell me if this is good. And so you get to write like, I don't know, it depends on how good the paper is, but you get to write something that's like, this is a fantastic paper, or this paper really needs a lot of work because I'm not supposed to say that it's trash. But it needs to do these things, or it's missing this thing, or like even things like you typoed. So that takes a fair amount of time. I like to also be on committees for conferences. My favorite is the scientific organizing committees, because then I get to read people's abstracts, and then I get to assign them talks. And that's a weird amount of power that no singular person should have, which is why it's a committee. And then last, I really like to mentor people. And so because of the wide variety of things that I do, which is fairly typical for academia, I can't really describe what my average day is. I can sum it up as like my average COVID day is I wake up and I sit at my computer for a very long time, and then I stand up and I go and walk my dog. That's my day during COVID. But during all of that, I'm writing and reading and coding and trying to get my paper to compile because it's a nightmare, and answering emails and all of that jazz. So I super highly recommend astrophysics as like a career path. But what we're gonna get to now is like my life, sort of, starting with high school graduation. And in there, you'll see that I left academia and then I came back. So it's a cool thing. So how did I get here in front of your computer screen? So in 2012, I randomly decided to move across the country to study physics. I'd like to tell you that I liked physics and wanted to study physics, but the real answer is I hadn't taken biology and I didn't know what to do because I liked dolphins. Yeah, but it's weird to study dolphins without having taken biology. And then I also liked math, but I didn't know you could study math. So we're now getting into like Mariah's backlog of what she understood about the universe, which was essentially nothing. So I decided to study physics, not because I knew nothing, but because I didn't know what to do. And in 2013, I started researching the dwarf planet Haumea, which, as I mentioned when I had my nice pendulum necklace, is the coolest dwarf planet. Like Pluto's awesome, like it has mountains and an atmosphere, that's pretty cool. But Haumea is like the fastest rotating large object in our solar system. It has a day of 4 hours that makes it egg-shaped. It has 2 moons. It has like no, I can't say that word, a lot. It has a lot of water ice. Like, it's a fantastic thing. Anyways, I started studying it for the purposes of needing to eat. I wish I could say that it was like, oh, it was so cool, I wanted to study it, but no, I just need money. And it ended up being fantastic because then I decided to also study astronomy and astrophysics. This was essentially like a why not situation. I already had to take, my school offered both degrees, and I already had to take most of the classes for astronomy and astrophysics, and I was already like, I don't know, neck high in student loans, so like might as well get the most out of it, right? So it was at this point near my graduation that I kind of got really burnt out from academia, which, especially with these stresses from the election, from the pandemic, from life in general, you might be feeling really burnt out from academia. Yes, know that I understand. I feel it in my soul. So I decided, as a lot of people in my class did, that I actually like was swearing off academia, but I didn't want to be jobless, right? Nobody does. And so I decided to test my skills at being an engineer. So I went and worked at Lockheed Martin, which, if you are currently feeling burnt out from academia / have decided that you don't want to stay in academia / have decided that you want to go into industry, there we go. I highly recommend Lockheed Martin. Lockheed Martin and other DoD contractors love physicists. Like, they cannot get enough of us. So it's you end up building this wonderful like set of skills which are very marketable. So if you're not like, if you're like, I don't really want to do science, like that's cool. You can just go and like do engineering. Yeah. So super marketable. At Lockheed Martin, it was actually challenging because I had been trying to get a job and they were like, what do you study? And I was like, physics. And they were like, we only want engineers. And so I like didn't answer that question eventually. And I was just like, I can code in 7 languages, like raise eyebrows 3 times. And they're like, you're hired. So I tried that. I didn't like it. Apparently, I like putting my effort towards discovery. And I think that's cool. Like, I like saying that I found a planet. I like saying that this one planet has like 0 atmosphere. This is enjoyable to me. It was weird because I also like, I have a secret clearance. And so I couldn't tell people about my work, which was really cool for like 3 weeks. Cause I was like, I can't tell you what I do, or like things like that. Like I have an NDA and I'll go to jail. But eventually it became weird because it was like I'd come home and like my fiance would be like, how was work? And I was like, oh, it was fine. I had a problem with a thing. And then I talked to a person and we solved it. And like, that was the level of detail I could say. And apparently that really affected me. So there are a lot of people that doesn't bother. And there are a lot of people that there are on projects that they can say more things about. Like I can tell you my project was amazing. It had to deal with satellites and lasers, which are a really cool combination, but that's all I can tell you. So I ended up graduating with my degrees and then was like, I didn't really like that. But I'm also still really tired and burnt out and I don't really want to do science. So I decided to just continue everything, like why not? So I started my master's at the same institution I got my bachelor's degrees. And then I also became an engineer at Northrop Grumman. So that was mostly, I wanted a reason to move back to the hashtag West Coast, Best Coast, which I realized on the East Coast you might not agree with, but the West Coast is awesome. Because it has no humidity and amazing sunsets. But so I moved to LA, lived there for a while. And then I ended up transferring to Penn State, and here we are. Like what year is it? 2 years ago, I got my master's, which was the official thing of you can now start teaching for reasons. And so I started teaching. I adore teaching. When I was an undergrad, I taught calculus, which is like a weird thing to say, and fencing, which is also a weird thing to say. But I realized that I really liked teaching, and I was very annoyed when I went to Penn State and people just kept being like, grad students don't teach. Okay, well, can I? Like, you only have to pay me like 1/3 of what you pay other people, and I will, like, my students will love me because I am fantastic. So please. And eventually, like, they're like, fine, sure, try. And it was amazing. So the only next step is I graduate in January. This is fingers crossed because like I have to defend my dissertation, which is always just a terrifying thing. And then the next step is to be employed somewhere. So currently applying to jobs, which nobody's told me meant writing 3 to 7 essays per job. But that's what it is. And so I've applied to like 20 out of like 65, and here's hoping.
All right. Well, good luck. So thank you so much. This was really fantastic.
Oh, thank you.
So I know that some students are going to be popping out sometime soon. They may have some other classes to go to, but folks can hang around. I'm going to stop the recording.